Apple devices contain a highly capable NPU known as the Apple Neural Engine, or ANE. An NPU is a neural processing unit, a specialized circuit designed to accelerate artificial intelligence applications. The ANE outputs between 15.8 and 38 TOPS. TOPS stands for trillion operations per second, a standard metric used to quantify maximum theoretical computational throughput. However, Apple restricts direct access to this hardware, forcing developers to route their code through CoreML. CoreML is Apple's public machine learning framework, used to integrate models into applications. The current target for high-performance optimization is the M4 generation of Apple Silicon. It represents the most advanced iteration of Apple's specialized hardware engines. Apple designs the CoreML abstraction layer to prioritize energy-efficient background inference tasks. Advanced developers, however, require raw, unthrottled throughput for custom transformer workloads. To achieve that throughput, developers have bypassed CoreML entirely, mapping a route to talk directly to the undocumented Apple Neural Engine framework. This chart shows the M4 ANE's energy efficiency. It achieves up to 6.6 teraflops per watt. This measures how many trillions of floating-point operations a chip performs per unit of power. This rating is roughly 80 times higher than enterprise-grade A100 GPUs. To utilize this computational power safely, we must map the private software stack and build a deterministic fallback bridge to catch execution errors. This technical mapping traces the pipeline from the ANE client XPC connection down to the rigid physical constraints of the hardware's SRAM. XPC is Apple's native mechanism for secure message passing between different processes, while SRAM is the small, highly fast static random access memory located directly on the processor die. Direct silicon access exposes the raw throughput of the ANE, but it removes the software guardrails that prevent hardware-level failures. The ANE software stack operates in a strict hierarchy. CoreML sits at the top, delegating to Espresso. Espresso is Apple's internal machine learning inference runtime that handles model execution across the CPU, GPU, and ANE. Espresso, in turn, interfaces directly with the private Apple Neural Engine framework. Within that private framework, the App ANE class acts as the low-level Objective-C interface used to compile, load, and evaluate models. The primary program format submitted to the engine is MIL. MIL stands for Model Intermediate Language, an internal format used by Apple to represent neural network computation graphs before they are compiled into hardware instructions. This diagram illustrates the rigid process boundaries separating the user code from the hardware. The client application does not execute the mathematical operations itself. Instead, it sends a MIL payload via XPC to a system daemon named ANED. This separation of concerns dictates that the daemon handles all hardware scheduling and queue management, capable of supporting up to 127 simultaneous evaluation requests. This is a shared memory logic diagram demonstrating how the CPU, GPU, and ANE all point to a single I/O surface block in RAM, bypassing the need for data copies. I/O Surface is a macOS framework designed to share hardware-accelerated buffer data across multiple processes efficiently. This zero-copy architecture enables a symmetric synchronization model utilized in production large language model pipelines. In this dispatch flow, the Metal framework handles the attention pass on the GPU, while the ANE calculates the feed-forward network. The feed-forward network is the multi-layer perceptron block within a transformer architecture that processes individual tokens independently. In this visualization of the synchronization mechanism, the ANE pauses at a wait gate. It resumes execution only after receiving a MTL shared event signal from the GPU, seamlessly resolving into the shared memory. Because the GPU and ANE coordinate directly, the host CPU is freed from coordination tasks, allowing it to focus entirely on KV cache preparation for the subsequent token. The KV cache is a memory buffer used in language models to store past token representations, avoiding redundant calculations during text generation. Addressed directly, the ANE operates as a decoupled zero-copy graph execution engine, functioning as an independent coprocessor alongside the GPU. Accessing the private API exposes developers to a minefield of undocumented hardware limitations. The defining architectural truth of the ANE is that it is a convolution-first engine, rather than a generalized matrix multiply unit. To achieve peak throughput, standard linear layers must be mathematically reshaped into one-by-one convolutions. Performance is heavily dictated by SRAM residency. This schematic of the A&E core shows data looping within the fast internal SRAM for fused operations, then spilling out to the slower external DRAM for unfused operations. DRAM is the larger, slower main system memory located off the processor chip. The hardware requires fused operations, like an inner product combined with a ReLU activation, to keep intermediate data localized. Failing to fuse operations incurs a severe DRAM bandwidth starvation penalty, causing graphs to run up to 250 times slower. The hardware also enforces strict spatial requirements, demanding a minimum tensor dimension of approximately 256. If a program falls below the spatial threshold, the ANIC-IR compiler will reject it. ANIC-IR is the Apple Neural Engine compiler intermediate representation, the specific subsystem responsible for lowering the model graph into raw hardware instructions. The final barrier for custom execution is the OX1D map rejection error. This specific error triggers when the hardware cannot map the requested tensor buffers into memory, either due to strict alignment requirements or a permanent rejection of the underlying graph structure. Bypassing CoreML involves a high-stakes trade-off. It offers high computational throughput, but only if the computational graph conforms to the engine's rigid convolution and fusion parameters. To maintain production stability on this undocumented hardware, developers implement a runtime bridge that intercepts these rejections and routes them to a safe processing backend. This system relies on the interception of the neural network's linear forward pass using a custom Go-based runtime hook. The decision tree begins with the runtime attempting a daemon-backed memory map through the _ANE client. This code flow diagram illustrates the silent failure handling protocol. When the primary ANE path hits a 0x1D map rejection error, it triggers an immediate fallback routing to the CPU. Following a daemon map failure, the runtime initiates a secondary fallback to the local _ANE in-memory model for localized execution. If the ANE completely rejects the graph, the math is routed to a final safety destination, executing on the Espresso CPU backend or the native MLX framework. Failing to manage these fallbacks properly exposes the system to physical dangers, specifically kernel race conditions. Unmapping an I/O surface before the ANE's DMA controller finishes its flush will cause a system sig-seg, or a complete kernel panic. The DMA, or direct memory access, is a hardware feature, allowing subsystems to write main memory independently, while a sig-seg is a critical segmentation fault caused by accessing restricted memory. To solve this, developers set a specific completion handler and utilize OBJSet-associated-object to prevent the handler's premature release by ARC. ARC stands for Automatic Reference Counting, Apple's memory management feature that automatically frees up objects when they are no longer actively referenced. The system utilizes the legacy interrupt path, labeled FW signal equals 0, ensuring the host CPU is only woken after the DMA flush is physically verified in RAM. Custom shims attempting to use the modern FW signal equals 1 path frequently encounter inference timeouts or hardware crashes. By combining aggressive subgraph interception with a deterministic CPU fallback routing, the MLX Go bridge creates a stable operating island on highly restricted, undocumented hardware. Running custom execution paths and training loops on the ANE proves that these limitations have always been a software support issue, not a deficiency in the hardware. By engineering this safety bridge, developers gain granular control over the execution logic previously hidden by Apple's frameworks. The ANE functions as a programmable, hyper-efficient substrate for high-performance machine learning.